All right, we have two videos today, a little bit of reading. I was going to go through a whole bunch of dry articles, but we're going to skip ahead. I'll show you. This stuff amazes me, and I think it will amaze you. How come it did not allow me to share my screen? There we go. All right, so big tech. Those of you here, stay, commented freely. They're welcome. Let me send out notes real quick for those of you in YouTube. You get the notes. If you're not in YouTube, go to patriotsoapbox.com. Go over to shows. It's in the menu tab. Go down to shows. If you click on shows, you'll find a banner that looks like this. It's big tech. You can get to the archive notes by finding the column or the section that says read, watch, think for yourself. And here we go. So the notes today were full of things like vagus nerve stimulation, backdoor brain hacking, a couple different patents, new psychiatric tools, apparatus and methods for nerve stimulation and related methods. So there's all these articles here that we may go through at some point, but not today. They're all here in the notes. We may cycle through these, but not today. Vagus nerve stimulation with antennas. Those look fun. And more nerve stimulation. Oh, this is nerve stimulation with something like the screen of your cell phone. Yeah, this is from Nokia Technologies. Nokia owns Bell Labs, basically. They purchased Bell Labs. Bell Labs has been hoarded around the telecommunications industries over the last approximately 20 years. Alcatel had them for a while. Lucent had them for a while. Alcatel-Lucent had them for a while. Those companies are owned by telecoms in countries like France and China. And Nokia is somewhere over in Europe. The country of its origin is escaping me at this point. Nonetheless, yeah, electronic implants and electromagnetic pulses are picking up where psychoactive drugs have failed. We will get into this at some point. Not today. We are going to watch a little TV. So the first one we're going to watch is Battel's grand vision for neurotech. This guy used to work for DARPA. And here we go. Maybe.
This next session kicks off a deeper dive into all the remarkable things going on in neurotech. We are privileged to welcome to our stage Justin Sanchez, Senior Technical Fellow at Battel, for a rare look behind the scenes at the work they are doing to improve brain function.
So thank you for the very kind introduction. It's a real pleasure to be here. And I'm going to share with you our grand vision. So when we're all really young, we aspire to what we might be when we grow up and get older.
All right, so just a refresher, we've seen this guy before. If you've watched Big Tech for a while, he used to work at the biotechnologies office in DARPA. He was an office manager there. Now he's moved on to Battel, and Battel does things like make nanotechnology that is designed to go into your brain and drop off genetically modified material to allow the brain to interface with wireless energy, whether it be light, sound, or electromagnetic waves, and then leave the steerable nanotechnology potentially in place for additional types of stimulation. They also are involved in many, many other facets of technology and development, and they work very closely with DARPA and the military and all of that. So you're going to see another component of what they do in the neurotech field.
And you might ask the question, well, maybe I'll be a doctor or a lawyer or an athlete, but you've probably never asked yourself the question, what do I want to do with my brain in the future? And it's amazing that we don't ask that question. The brain is our most valuable possession, and it's the millions and millions and millions of neurons that are in your brain that give rise to all of the behaviors that help you to become what you ultimately want to be in the future. But there's one catch in all of this. From the dawn of time, our brains have been trapped inside of our bodies.
Now, there's an interesting idea to contemplate. From the dawn of time, our brains have been trapped inside of our bodies. Well, technically, he's correct. Physically, your brain needs to stay in your body, otherwise you don't live. But let's see what he has to say.
Okay, and it can limit the potential of what our brain ultimately might do. So what I'm here to pose to you today is a very different question. And that question is, how do you want to connect your brain today? So think of the possibility of opening up the potential of your brain to not be stuck in your head anymore. And that aspect of connectivity is so important for helping us to realize our hopes and our dreams and what we may become. And that may play a huge role in age or ability or even injury. So let's think.
Yep. Connecting your brain, getting your brain out there, allowing your brain to do more things beyond managing your bodily functions.
Think about that idea of connectivity. Let's say after you've had a spinal cord injury, your brain becomes disconnected from your body. What if we can rebuild that connection and help somebody to move again? Or what if you're an athlete or you're aspiring to be an elite athlete, you need a little bit of help in order to train a little bit more effectively or efficiently? Make a huge difference in connecting your brain in a very different way. Or what if you're getting a little bit older in life, you're an executive, you're in a meeting, you need a little bit of a boost. Maybe you can unlock the potential of your brain in a very different way in order to help you to do that.
Those are very elegant ways of saying, let's tap into your brain or your nervous system and electrify it, for example, to stimulate it, to enhance, increase, or change your performance.
So what's the game changer in all of this? Again, sounds like an interesting idea. The game changer is neurotechnology. And for those of you who have never seen neurotechnology, never heard about it, let me explain. Neurotechnology is an emerging technology where you can place a miniature sensor either in or on the brain. You can record from hundreds to thousands of neurons in real time. You take that moment-to-moment information, decode it with advanced artificial intelligence to determine what those signals actually mean, and then you send those commands or signals out in order to produce a particular behavior.
Okay, well, he kind of just broke it down in a simplified fashion, right? Some kind of a sensor monitoring your brain waves, complex algorithms taking those raw signatures, making sense out of them, and then translating some usable function. Now, he implied you needed a sensor in your brain, something like that. That's what he's going to show you. Ultimately, the question is, do you need to have a sensor in your brain in order to understand what's going on in your brain? And I submit to you that answer is no, on many different levels. We've looked at a few over the last few days. The earphones that have the same types of sensors necessary to pull the electroencephalography straight out of your ears from your brain. A watch that can do this wirelessly through transcranial magnetic stimulation and or through electrodes placed on the skin. A watch can pull this out of your brain. And after this video, I'm going to show you another video of a CEO of a company that Facebook recently acquired that is doing exactly what I'm just saying to you. Being able to pull your brain electrical activity straight out of the muscles in your body. Let's continue.
And while you may think that this is a technology of the future, it's very much a technology of today. So prior to my joining Battelle, I was a former office director at the Biological Technologies Office over at DARPA. And I would like to share with you some of the foundations that we pioneered in our work in neurotechnology. And speaking of pioneers, the people that I'm going to show you in this video, again, they're the real people that change the world here. These individuals are living with spinal cord injury. They all have these neural interfaces in their brain, and this is what they can do by just thinking about performing an action, and it's carried out through the neurotechnology. So here it goes. So this is 2012.
Baby, I want to hold your hand.
So that's Tim. He's paralyzed. His girlfriend says, I want to hold your hand. He's controlling that robotic arm just by thinking about it.
The highlight was 45 minutes ago. I got to use a robotic arm for the first time, and I got to reach out and touch somebody for the first time in 7 years.
Okay. Huge. And the applications, obviously there's great benefit to these applications. So that's something of note. Here we go. 10 months later.
All right, 2013.
I can move it up and straight down and left and right and diagonally. And I can do a fist bump if you'd like.
That's amazing.
There's not a lot I can do from this position in my life physically, but now I'm doing so much. It overwhelms me. I'm so glad I did this.
So that was in 2013. She's having a conversation while performing complex movements with a robotic arm. Right? There's a brick on top of her head that's tied into an electrocardiography ECOG implant, a Utah array probably, more than likely. This was in 2013. Complex algorithms reading the signaling straight out of her brain, translating it into a robotic arm so that it moves relatively fluidically and interfaces with the world around her. Hashtag nanotech. Do we even need the ECOG anymore? And the guy that's talking works for a company that is delivering nanotechnology to soldiers' brains, or is working on programs to deliver nanotechnology to soldiers' brains to do this very thing without any invasiveness. A simple round of shots before you go into country somewhere when you're deployed around the world. Nobody will know. It's just another shot. Military, take your shots. They love you.
So that's Jan. She's really special. And she said, hey, I also want to control a virtual flight simulator just by thinking about it. And she's banking this aircraft, virtual aircraft, just by thinking about it. Now, we ran this experiment in reverse. Nathan is paralyzed, can't feel.
Middle. Index and middle.
Writing signals into his brain. He can say which fingers we're pressing on.
Did he just say writing signals into his brain? He did just say writing signals into his brain. So not only are they reading signals, they are able to write signals into the brain. Things that make you go,
Now, you can also do this to peripheral nervous system.
Oh my God,
Okay.
I love that word. God, that is so cool.
All right, 2015. And then lastly, we not only do this for movement and sensation, but also memory. So writing memories into the brain. This is
okay, writing memories into the brain in 2015. In 2015, they are able to write memories into the brain. Memory implantation, folks. And we have technologies that are patented already publicly that discuss being able to interface with the brain, particularly in the, I believe it was the occipital cortex, the memory centers in the brain, to transmit basically conduct synthetic telepathy, mind reading technology. Thought transfer, I think, is the term in the patent from Freer Logic. using transcranial magnetic stimulation with power supplies, something that fits inside of a watch. So just because people with an electrode array in their brain doesn't necessarily mean that the buck stops there. Oh no, oh no. Memory implantation, that's where we were. Let's continue.
Recall 12 words with no stimulation. This person got through 3 of the 12, and we've all experienced this when it's hard to recall something. We do the old face palm, right? Really tough. Now with neurotechnology, with stimulation into the brain, here's those 12 different words.
No kidding. All of them.
And that was a breakthrough moment for us.
He said, I had a real clear picture in my head. I could see with the stimulation. Let's see what Justin has to say.
We knew we were writing the right signals back into the brain so that it truly had a positive effect. So again, technology of today and a technology of the future. You can see how those foundations are going to change the world.
They were writing the correct signals back into the brain. The technology of today are the foundations of the technology of the future that are going to radically change the world. So here we go.
Again, I want to share with you one last pioneer in all of this. And this pioneer was one of the people at Battelle that really helped to change the world. And again, this talks all about connections. How do we reconnect our brain? And for this person, his name is Ian. He's also living with spinal cord injury, but he's very different than the other people that I share with you. He really wanted to reconnect his brain to his body, his own arm. He wanted to reanimate his own arm and his hand. So what the talented engineers at Battelle did was they developed a new technology, a sleeve technology that could go on his forearm that could stimulate his own muscles and reanimate his hands. So let me share with you his story.
What did he just say? He's going to put a sleeve on his arm and reanimate his hands. Wait a minute. Now, if you remember the last show, we were talking about electromedicine and electroceuticals and micro and nano-sized devices that are going to go in and attach to your nervous system. And the National Institute of Health with Dr. Fauci sitting in the audience in approximately 2017, 2018, mapping the entire nervous system to such a degree that they understand the uniqueness of said nervous system person to person in order to provide personalized therapies. And this guy's talking about a sleeve that's going to go over the arm to reanimate a hand, obviously through interfacing with the peripheral nervous system. Let's continue.
Before we dive into the details of how it all works. Okay, so here's Ian.
I had just finished my freshman year of college. I was out in the ocean and I dove out and into a wave, something that I'd done many times before. I dove into a sandbar that I'd drifted in, which fractured my spine and damaged my spinal cord, and that left me as a C5 quadriplegic. I kept asking the doctors, what can I look forward to in the future? One of my doctors said, hey, we want to try this muscle stimulation device. It really sounds like it's something out of a science fiction novel.
I want to go back and show you what the archaic prototype is that they're showing you here. Look at all of the little circles wrapping around this person's arm. This is a test device. You will see what they're going to showcase for you. This presentation was done in 2020. January, I believe, was 2020 was when this guy delivered this presentation. And you can go to Battel's Neurotech site, and you will see this sleeve on the site. But this is a prototype for being able to take measurements, every one of these little circles, taking measurements of the muscle activity and or writing signals into the muscles / nerves, because there are nerves that proliferate throughout your muscles in order to get things like very fine precision motor control and dexterity. Something a surgeon would need, or an artist would need, or even you if you wanted to pick up a fork and not stab yourself in the face while you're eating a steak.
Get something out of a science fiction novel, reconnecting my mind to my body.
Okay, so huge challenge. But again, the talented engineers at Battel brought it all together. The brain interface, the decoding algorithm, the sleeve technology that can reanimate his muscle. So you might be asking, how does this make a difference in Ian's life? Well, first step is just get movement going back to the hand. So in this video here, you can see he can open and close his hand, all right? Again, it's huge for somebody who's paralyzed. Again, kind of locked into a particular state, neurotechnology can make all the difference in the world. What about doing something like stirring your coffee in the morning? We all take this for granted. For a person like Ian, he can't do it. He needs something else. So again, the engineers set up the initial conditions in order to, think about controlling his hand in that way, and the system's able to do that. Again, it's not all about just the basics in everyday life. You got to have a little bit of fun too. So they also reanimated Ian's hand so that he could play Guitar Hero. So again, he's playing Guitar Hero in real time, just using that direct brain interface.
This is not a prosthetic arm, folks. This is flesh and blood. The information collected from projects like these lead to having a common database of algorithms that understand how to write information into the nervous system of a human in order to animate the human. And the only question at that point is, can they override the impulses of a perfectly functioning human with these known algorithms and techniques / technologies / nanotech / 5G? We'll get into how 5G plays into this as time goes on. Directed energy systems that converge and make unique resonant characteristic waves that do things like regrow nerves, stimulate nerves, resonate parts of the brain, regrow portions of brain and brain circuitry as a result of traumatic brain injury and lesions in the brain, or lesions or damaged nerves. Yes, there are patents for that from a startup company that Google is now funding called BrainQ, believe it or not. Israeli-based. Hashtag tech transfer China. Let's continue. I'm digressing.
Okay, so it's remarkable, it's life-changing, it's going to change the world for the future for a lot of other people. So again, at every step along the way here, we learned a lot. So at Battel, we're really trying to push these into real products, and we've learned that there's a few elements that make these products really functional. You have to be able to analyze and decode those signals in real time. We can do that. We have technology to do it. The way that you connect and how you connect should make a difference in that person's life. You need to perform actions and behaviors that ultimately are valuable and provide a meaningful function. And lastly, and again, this one's very important, it must also adapt. Remember, the brain is the ultimate adaptable kind of system. We have advanced AI that enables our systems to also adapt with the user.
We have advanced AI systems that allow our system to adapt with the user. Personalized therapy. Thank you, National Institute of Health. Thank you, Dr. Fauci. Thank you, GlaxoSmithKline. Alex Azar, if you're listening, I know you know, and now you know I know you know just what the hell is going on.
So while we've laid the foundations of all of this and we're pioneering this for the future, you might ask the question, well, what's over the horizon? What are the new products that might be coming out? Well, technologies like this, you can think of advanced security, right? Maybe the unique patterns of neural activity could be used as a security code, or maybe more immersive kinds of gaming, right? Imagine you have a gaming experience with a neural interface or a sleeve kind of interface, maybe even brain-controlled vehicles. There's a lot of things here at CES that is looking at autonomous vehicles, but maybe a brain interface with that would change human-machine teaming. And lastly, sports and athletics. And this is an area that we really think is going to make a difference.
So human-machine teaming, perfectly stated, elegant, almost seductive, as it relates to DARPA and the military apparatus, fusing AI, drones with the human weapons system, augmentation of weapons platforms means at this point fusing humans into an automated environment that works synergistically with machines. And that will trickle down out into a place called home, where you may become the drone.
While everything that I've shown you up to this point might feel kind of like in a medical domain and out of your reach, in the area of sports and athletics, there's something that we think you can grasp today. So we'd like to do something really unique here. We're going to do a demo for you, a live demo, and it's something that we call muscle memories, okay? It's a new way to learn from the pros. All right, so some of you in here might aspire to be a golf pro, and you know how hard it is to actually do that. And there's one aspect of the sleeve that I did not tell you about up to this point. It can not only stimulate muscles, but it can record from muscles. So imagine putting this sleeve on a golf pro, recording their muscles so that they have that kind of perfect swing. And if we could record those moment-to-moment activities and store them in a database, we could potentially do the following.
Are you seeing what I'm seeing? We're going to take biometrics, in this case, muscle activity. We're going to record it. We're going to store it into a digital library, and then we're going to sell it to the highest bidder.
I was just about to say who can
it.
access it. Sorry.
Say again?
I said I was going to say who can access it.
Yeah, well, cybersecurity is kind of the most important thing now.
Agreed.
So we just wait until we get to the next video. Just wait. Anyway,
I'm on the edge
let's
of my
see
seat.
what's for sale. Go ahead.
No, I said I'm on the edge of my seat. So is chat.
Yeah. Yeah. Let's see what's for sale.
Okay, perhaps we can write in those muscle activities into an amateur's arm to help them have a more pro-like swing. So you might say that this sounds impossible, but we're going to do a demo live for you here today to show you how it all works. So if the team could kind of come up, and as the team is coming up here, we also have a volunteer from the audience. So I believe your name is Patricia, right? So Patricia's going to help us out with this. So give Patricia a round of applause. Okay. And what I also didn't tell you is that I am wearing one of the sleeves here today, okay? So let me show you what that looks like while we're all getting set up. All right, so this is the sleeve system, okay? This is what it looks like. And as you can imagine, I've been wearing this all day here. I had it under my suit. And there's 160 both sensors and stimulators in that sleeve. It conforms to my arm. It's really comfortable. And again, it can look at all of the muscle and nerve activity in that sleeve.
It can look at all of the muscle and nerve activity. Reading and writing. Brain computer interface, overriding the nervous system of what you're going to see of a perfectly functioning human. But but it's okay. It's just a gentle golf swing. Don't you worry. Don't you worry. It's just a gentle golf swing. It couldn't be anything else.
Again, Battelle designed, and the engineers really made this thing functional. It's an early phase design from the team here. And again, you just get it plugged into this device, okay? And let me just tell you a little bit more about the demo that we're going to be doing. Okay, so again, for those of you who are not golf pros, the angle between the club face and the ball, right, how square it is makes a huge difference in how you actually hit the ball. Okay, and if it's not square, you can either cause the ball to slice or to hook. So as you're learning to play golf, okay, your coach might teach you to try to rotate your hands in certain ways in order to prevent those slices and hooks. And what we've actually programmed here, what Patricia's going to do, now don't hit the button yet, okay?
We're going to move you back a little bit so that the camera can pick this up.
Yeah, okay. Again, let me just click one more part of the slide. Anytime, anywhere, we can have some pre-programmed patterns, right? The pro patterns, and they can be sent directly into my muscles, okay?
It's okay. We can record somebody's muscle activity or generate it artificially with enough in a database where we get enough samples, and we can just go ahead and inject that in your nervous system and call it fun and games.
And we've already pre-programmed some of these things into the tablet that's right over there. Don't press yet. And we can make these kind of online corrections as we go, all right? Now, I can't see what Patricia is programming into my muscles and my nervous system. So again, you'll just see the response of my muscles as she does this. So are you guys
hearing this? Programming into my muscles and my nervous system online, meaning could potentially be used over the internet. Hashtag Huawei.
Ready? So I'm going to kind of get in position here, and she's going to press a button.
You go.
All right, and that caused my hand to kind of rotate in that direction, okay? She can pick another one. You can try pressing again. You see it rotates back. All right, again, I'm not doing this. It's being written directly into my muscles. You can try one more if you want to do it. Okay. There's another one. You want to do one more? There it goes, and rotates that way. So again, imagine doing that. I mean, we're like a few feet away from each other. This could potentially be done through the internet, could be done halfway across the globe. It changes the way that we connect, right? Again, it's all about connections. This is technology that can do that for us.
I don't know how better to illustrate to you just where we are and what we're doing and the importance of applying the Constitution and the Bill of Rights to the internet and getting out of this paradigm of the Internet Bill of Rights that are being discussed between big tech and big telecom, and leaving the discussion there because they're the quote unquote experts. They don't give a crap about you. They want your money. They want your work and your sweat for nothing, and then they want your money. They don't care about you.
For us, all right? So one last piece of the puzzle. Those are online corrections that you can make as you're learning how to do, let's say, a pro swing. Let us take it one more step, okay? So the team set up a few golf balls. We can come up with patterns that can do a whole swing, all right? And again, for the golf pros out there, we know that a putt is not necessarily wrist kind of motion here, but just for demo, you can see how we can do kind of the full swing end to end. So let me get into position here, and Patricia's going to press the button, and hopefully it'll all come together. All right. Again, that was all just from the stimulation alone. I'm not doing anything, and you can try it again if you want to go. All right. So again, it shows you how neurotechnology could potentially change the world. So everybody, please give Patricia a big round of applause for helping us out there. Okay? So I just have one more slide for you. So we started this whole conversation today about your aspirations for the future, what you want to do. And I said, thinking about how you might use your brain, how you might connect your brain could change the world. So I pose one final question for all of you. How will you connect your brain in the future? And I would say the answer to that question ultimately is in your hands. It's what
It's in the hands of Twitter, Facebook, Google, AT&T, Verizon, Sprint, T-Mobile, Microsoft, Amazon. It's in their hands at this point. So he's lying. Let's move on. Oh, okay. That's not normal. Let's skip ahead and see if it'll catch back up.
Organ. And while many people are fascinated by the brain is an amazing and complex organ. And while many people are fascinated by the brain, they can't really tell you that much about the properties about how the brain works because we don't teach neuroscience in schools. And one of the reasons why is that the equipment is so complex and so expensive that it's really only done at major universities and large institutions. And so in order to be able to access the brain, you really need to, dedicate your life and spend 6.5 years as a graduate student just to become a neuroscientist to get access to these tools. And that's a shame because 1 out of 5 of us, that's 20% of the entire world, will have a neurological disorder.
Yep. Well, it'll be more than that. Anyway, he gets into his backyard science stuff, and then he brings somebody up on stage. So we will skip ahead.
Your brain, have you had this before?
No.
Okay, all right, I need you to stick out your arm for science, roll up your sleeve a bit, all right. And so what I'm gonna do, I'm putting electrodes on your arm, and you're probably wondering, I just said I'm gonna record from your brain, what am I doing with your arm? You have about 80 billion neurons inside your brain right now. They're sending electrical messages back and forth and chemical messages, but some of your neurons right here in your motor cortex are gonna send messages down when you move your arm like this. It's gonna go down across your corpus callosum, down onto your spinal cord, your lower motor neuron, out to your muscles here, and that is electrical discharge. It's going to be picked up by these electrodes right here, and we're going to be able to listen to exactly what your brain is going to be doing. So,
so that Battelle sleeve was just a whole bunch of those electrodes that you're seeing right there. Many, 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 many of them on a nice, sleek sleeve. This guy is using the same fundamental principles, but using very, very cheap materials in order to get them in the hands of more and more people so they begin to understand what neuroscience is about. But wait, it gets better.
Turn this on for a second. Have you ever heard what your brain sounds like?
No.
All right, let's turn it on. So go ahead, whenever you, go ahead and squeeze your hand. All right, so what you're listening to, so this is your motor units that are happening right here. Okay, so let's take a look at it as well. So I'm gonna stand over here, and I'm gonna open up our app here. So now I want you to squeeze. Yeah, so right here, these are the motor units that are happening from her spinal cord out to her muscle right here. And as she's doing it, you're seeing the electrical activity that's happening here. We can even click here and try to see one of them. So keep doing it really, really hard. Yeah, so now we've paused on one motor axe potential that's happening right now inside of your brain. Okay, do you guys want to see some more?
I want to see some more. I want to see what else this guy's going to show us. Keep in mind that anything you see here can potentially be done over the internet. And I postulate to you without any of these bulky wires. Just what was Charles Lieber up to?
All right. That's interesting, but let's get it better. Okay, I need one more volunteer. Okay, what is your name, sir? Miguel, all right. You're going to stand right here. So Miguel, when you're moving your arm like this, your brain is sending a signal down to your muscles right here. I want you to move your arm as well. All right, so your brain is going to send a signal down to your muscles. And so it turns out that there is a nerve that's right here that runs up here that innervates these three fingers. And it's close enough to the skin that we might be able to stimulate that. So that we can do is copy your brain signal that's going out to your hand and inject it into your hand so that your hand will move when your brain tells your hand to move. And so in a sense, she will take away your free will and you will no longer have any control over this hand, okay?
Did you hear what this dude just said? I know he's making a joke.
And they all
Imagine what the applications of this would be in a no contact environment. Being able to use your brain to control somebody else's body. Oh, there's a patent for that. AT&T's got one for it. Want me to show it to you again? Tell you what, you can go to my Twitter and it's pinned to the top. It's been done, folks. It's been done. So here we go.
You with me? All right, so I just need to hook you up. All right, so I'm going to find your ulnar nerve, which is probably right around here. You don't know what you're signing up for when you come up and... So now I'm going to move away and I'm going to plug it into our human-to-human interface over here. Okay, so Sam wants you to squeeze your hand again. All right. Do it again. All right, perfect. So now I'm going to hook you up over here so that you get the stimulus. It's going to feel a little bit weird at first. This is going to feel like you know, when you lose your free will and someone else becomes your agent, it does feel a bit strange. I want you to
when you lose your free will and somebody else becomes your agent, it feels a bit strange. Well, yes, it does. The question then becomes, is your new agent of this world? What are we building, folks? I'm talking the species. What are we building? When you look at the last 100 years, what are we watching right now? We're watching the human becoming an empty, open vessel through the large picture here, through the erosion of the social fabric and of the moral and ethical components that make a society successful versus unsuccessful or disruptive or destructive. We have that component. And then we have this. And what this is a simple illustration of the ability and to some extent, a mastery of overriding the mechanical components of the human organism. Empty vessels for what? Are we free? Are we going to be free? Or is our species going to become relegated to livestock, truly as livestock?
Relax your hand. All right, and Sam, you're with me? All right, so you're gonna squeeze. I'm not gonna turn it on yet, so go ahead and give it a squeeze. All right, so now, are you ready, Miguel?
Ready as I'll ever be.
Okay, so I've turned it on, so go ahead and turn your hand. Do you feel that a little bit?
No.
Okay, do it again.
Oh, a little bit.
A little bit. Okay, so relax. No, hit it again. Okay. Oh, perfect. All right, so relax. Do it again. All right, so now... All right, so right now, your brain is controlling your arm, and it's also controlling his arm. So go ahead and just do it one more time. All right, so that's perfect. So now, what would happen if I took over my control of your hand? And so just relax your hand. What happens? Nothing. Why not? Because the brain has to do it. Now you do it again. All right, that's perfect. All right, well, thank you guys for being such a good sport. This is what's happening all across the world, electrophysiology. And we're going to bring on the neural revolution. Thank you.
Welcome to the real world. So, we have another video. But before we go to that video, we are going to look at this real quick. Facebook acquires Control Labs, brain computing startup. Control Labs, CTRL Labs. This was September 23rd, 2019. This was published, updated on the 24th. Facebook on Monday announced the acquisition of Control Labs, a New York startup that specializes in allowing humans to control computers using their brains. Size of the deal was between 500 million and 1 billion. The CEO, Thomas Reardon, I'm telling you this off of memory, used to work in the R&D department at Microsoft. So that's just one. I mean, there are many. I mean, there's one from The Verge, VentureBeat, Engadget. They all write about the same thing, right? This happened last year, September. Facebook now owns this company that we are going to watch a video about. Keep in mind everything we've seen so far. Sensors, reading and writing, and arithmetic necessary to interface with the brain, both input and output, and the ability to override somebody else's impulses and muscles using the very same type technology. And off we go.
Greetings. I want to talk to you about Control Labs and the novel breakthrough work we're doing on a new kind of neural interface. We started the company to address this problem, this yawning gap that machines and computers expose between human input and human output. You have a phenomenal ability to take in information in the world, visually, auditorially, from touch and proprioceptively as you move around. You're actually pretty terrible at output. And every new wave of machines and experiences exposes this deeper and deeper problem. This is probably 5 orders of magnitude if you measured it in some scientifically cohesive way. We want to break through this and expose human output at the same level as your input stream.
So that's what this company is all about. Being able to expose the output as efficiently as the input. So reading the output as fast or better than what can be input. And when you think about the majority of the input being sight and sound, that's quite a bit of information. So here we go.
And we want to do that in a way that isn't just about sort of this abstract notion of increasing your bandwidth, but also increases your facility. I love this picture because it mixes together this suicide act of this person trying to text while driving with driving itself. Now, driving is actually kind of an enjoyable output task. It's something you do by moving. You need some feedback to control it. It's actually very pleasurable. Texting, especially since 2008 with the iPhone, is a damn frustrating experience. We regressed as a species in 2008. It's not like we're more facile with the phone. I want to make typing, text production, controlling anything around you, robots in an industrial setting or in a home setting, your immersive experiences in VR and AR, I want those to feel as fluid and easy as driving, something you learn naturally and adaptively. I wanted to talk to this audience in particular about this. So some of you may not be old enough to remember the introduction of the IBM PC in the early 80s. What I thought was funny was IBM's choice to use the Charlie Chaplin character, the Tramp, to introduce it, to kind of humanize it, when it's actually, if you know about Chaplin, it was like, made a whole career out of sort of making fun of technology.
So what do you see there, folks? Little symbolism, that red rose. I've seen that before. I bet Mo could tell us what that is. but that's there for a reason. And then over to the right, you've got what looks like Minority Report. Minority Report. What was that? That was about pre-crime, wasn't it? Predicting crime before it happens. Don't you think that that's going to be infinitely more possible if you have real-time analysis of people's brains? Do you think it's probable to elicit crimes, create crimes, if you had access to people's brains? Hashtag mass shooters.
And there it is with that keyboard. There was no mouse. It was basically a 19th century device, vaguely updated. And then, of course, in more recent times, we had the first attempt to kind of show a popular version of immersive experiences, or an artificial reality experience, an augmented reality experience with Tom Cruise in Minority Report. And here, one of the apocryphal stories perhaps is that he had to shut down filming during that movie after about an hour of filming and doing all of this crazy stuff because his arms were too tired. We call it gorilla arms, from basically running a spreadsheet. That's not the kind of immersive experience we really want. We want you to have high facility, and we want it to feel effortless, not effortful.
Right. So that idea, but without moving your body. So what's that look like? Well, let's find out. I mean, they're doing this kind of stuff with people that can't move their body already, right? They just put a brick on their head that ties into a Utah ray. I mean, that's what we think the climax of this technology is at this point. Never mind that yesterday I showed you around this time, actually. Maybe it wasn't yesterday. It was the last show we did. It was Friday. Air Force Research and Charles Lieber. Nanotechnology infusing and integrating into neurons in order to create a input-output state at the neuron level, the cellular level, creating cyborg tissues. Anyway, let's continue.
So I'm going to talk to you about how I think, how we map out how you actually work in the world today and how you work with devices and computers today. Your brain, this forebrain up here, is actually really a lot bigger than just that. It's connected to your spinal cord. And your spinal cord is what carries information out to your muscles. Motor neurons up in the forebrain connect to those lower motor neurons in the spinal cord, and they turn muscles on and off, and that's how you move in the world. But then further, that's how you actually interact with digital experiences, with mice and keyboards and a touch screen or a Kinect as you move around, or even a microphone. All of those are just mechanical transducers. They take your movement, which is very slow, and transduce that to something that allows you to control this myriad field of digital devices,
You see where this is going? If you don't yet, don't worry, because he'll take you all the way. Just remember, Facebook now owns this. And this is not the only company doing this. We just saw Battelle doing the very same thing. Please stay as long as you can stay awake. Oh, make sure you're wearing your smartwatch.
Experiences. Whether it's VR, whether it's a robot or a drone, whether it's the IoT thermostat on the wall. We think there's a better way and a more general way of approaching this problem of control, of increasing your facility and increasing your output. And we call it intention capture. And yes, that's specifically meant to evoke motion capture. So I want to give you a hint of how intention capture works. I'll go a little bit deeper on it, and then we're going to show you some demos of actually how we do it. So what if instead of actually building these devices that transduce our movement in the world, instead we actually just listen to the electrical activity of those motor neurons, those neurons that are turning muscles on and off, and we directly translate that into control over devices.
Listening to the electrical activity of the motor neurons. Well, that's the very same thing we saw with the first video with Battelle. And those motor neurons are what was firing when that female was controlling that male's arm in the second video, connecting with the brain. So reading those electric signals. Here we go.
Just get those intermediate devices out of the way. Get the muscles out of the way. Your neurons are crazy fast and crazy high bandwidth. That's what we tap into. It allows us to now imagine new kinds of interaction that go beyond your actual physical body. What it would be like to have 6 fingers. Or what it would be like even further to kind of get way out there and say, what would it be like to have 8 arms and to control them as if you were an octopus? The only way to do that is to tap into the immense capacity embedded in your brain, but which is constrained by your muscles. So I want to go into how we do it here. I'm going to do a little bit of neurobiology. So we had to decide what kind of neural interface do we want to go do. We decided first, we're not going to go and drill into the skull and listen to neurons up there. But what we did want to do is take advantage of something about motor cortex, which is that, and he showed you the brain there, now this is a slice and a view on the other axis to look at the way cortex is arranged. And this is a famous picture called the motor homunculus. And what this does is it gives you a sense of how much of your brain is dedicated to what parts of your body. And within this, you'll notice the largest density of neural output from your brain actually goes to your hands.
So this is a very known image, very well-known image. And what he's basically postulating here is that the primary function of your brain, outside of keeping yourself alive, your body alive, and your organs working without you consciously having to control them, is controlling your output, control of your muscles, your musculoskeletal system. And that's what this illustration is. This is what he wants to tap into. Here we go.
The second most goes to your mouth, but your hands are the most skillful part of you. That shouldn't be that surprising to many people here. And it actually, the input to your hands from your brain dwarfs any other part of your body. It allows us to put this device on the wrist and actually extract the highest density of nervous signals in your body.
Do you see that? Do you see what's on his wrist? That is what he's demoing in 2019. That's what he's demoing in 2019. That's what's public. That's not what's probably the best. That's what's public. And if you look at the patents that Apple has, for example, they have conductive watch bands, as does Fitbit and others, that have electrodes around them. There are medical devices that have electrodes around the band. And that's all this is. It's all this is. They have conductive polymers, conductive plastics. They have nanotech that can be infused into plastics that create complex electrodes. Case in point, we could go back and look at the earphone patents that discuss things like conductive polymers and intricate metallic structures embedded into elastomeric type materials that would be able to do the same types of things that this guy's about to talk about. I want you to notice the form factor. That's all. Here we go.
So we take that down, those motor neurons and the motor cortex, again, project down to the spine. Those in turn relay to motor neurons in the spine. These are the single neurons, the largest cells in your entire body. It goes all the way out, courses out, connects onto the muscle, and we're detecting it by the electrical response of the muscle. And what we do is we have this array of electrodes here, and we're able to deconvolve this very complex mixed signal into the component signals, which are the individual activity of individual muscles. And from that, we basically get a map of anything you would normally do in the world, whether that's typing on a keyboard, swiping on a phone, moving a mouse around. That's all done by some combination of actions of individual muscles in the hand. There happen to be 14 in the arm that control your hand. Well, that's kind of interesting, but that just allows us to effectively virtually recreate everything you do today in the world. What we really want to do is go a little bit deeper. Inside the muscle are actually connections from hundreds of motor neurons, and this is the neurobiology I was warning you about. So when you actually go into the spinal cord, you'll notice there are these 3 motor neurons in the spinal cord, and they're connected to the muscle, the single muscle.
So here we go. Not only is this thing able to read what you're physically doing, but it reads so much more. It allows an interface that's so much more. So he's going to kind of explain a little bit of the mechanics behind it, and then what some of the fun little frilly options are. It doesn't stop where he ends, though. This is just a cute and fluffy corporate presentation.
And actually, there's fibers in the muscle that receive input from a single motor neuron, these red ones, the blue ones, the purple ones. That collection is called a motor unit. Whenever a motor neuron is active in the spinal cord, it sends off something called an action potential. It's the 0 and 1 of the nervous system. It's how the code is generated. Whenever that 0 or 1 is sent from the spinal cord, that cluster of muscle fibers all respond at the exact same time. And with very clever signal processing and ML algorithms, we're able to actually separate out not just muscle from muscle, but neuron from neuron.
So his company, which has now been procured by Facebook, is able, with complex algorithms that are likely of the same nature that Battelle has, complex, diverse, able to adapt to a user, using machine learning, constantly evolve, are able to single out a neuron and distinguish it from a different neuron. Not clusters, not nerve bundles, but neuron to neuron. That level of sensitivity with a device that has almost an identical form factor to an Apple Watch.
So that now I no longer have to think about my muscles controlling my hand. I can now think about hundreds of neurons reassigned to control anything.
Yeah, he just said reassigning your neurons to control anything. Sky's the limit. What do you want to do with your brain?
The last thing I'm going to do is try to marry this to an ML concept that I'm going to try with you for the first time. The goal here is not just to capture the motion that would result from the activity of a neuron. We want to capture the underlying intention. And you'll hear me say again and again, we don't care about the movements you make. We care about the neural signals underlying what would be movements. The heart of this and what our company is basically staffed by are machine learning scientists who are taking the signals from individual motor neurons, which exist in their own network, and directly feeding those into a synthetic neural network, a DNN, if you will. And those neurons these synthetic neurons try to create a mapping to your intention. That intent.
So this company is working very diligently on mimicking the biological neural networks that we understand as the brain and the nervous system, and putting them into a digital form so that there is a synergy, there is a convergence, digital neural networks, DNNs, using machine learning, ML, which is his cute little fluffy way of saying machine learning. Marrying these two together by creating digital neural networks that mirror the biological ones that we all have.
Intention would be me moving up or down, or moving the cursor up or down. But now try to take that to a more complex space, which we'll show you in these videos in a moment. And what we're trying to take advantage of here is not just grabbing your intention, but giving you the feedback, just like that steering wheel would, the feedback that allows you to rapidly train yourself to control a new thing that doesn't have any mapping to your body whatsoever. We call that adaptation, and that's really kind of the secret sauce embedded in our technology. This ability for this artificial neural network to drive feedback to your nervous system and get into a tight feedback loop such that your neurons are directly interacting with an artificial neural network, which is then directly feeding back to you and allowing you to gain rapid control.
Notice how he said allowing you to gain rapid control. But what he also said was that this adaptive neural network is adapting to understand your intentions and then can interact with your nervous system to create intentions, basically, providing feedback, right? And he likened it to driving. How could a car control me, right? It's so benign. It's so innocuous. Keep in mind, we just saw the very same family of technologies writing into the nervous systems of humans, perfectly functioning humans. And you have software like this being developed, adaptive, intuitive, artificial neural networks that are designed to merge and marry with the biologic nervous system, the biologic neural networks, to create a synergistic, interactive reading and writing interface to take rapid control.
So we say that intention capture allows us to decode the activity of real neurons, your motor neurons, using digital neurons. We have two different kinds of control we talk about. We talk about myocontrol and then neurocontrol. Myocontrol is when you're moving. Neurocontrol could be when you're moving, but it's really just the activity of your neurons. Myocontrol allows us to redo anything you would today virtually. Type, move a mouse, move a joystick, drive a car. Neurocontrol allows us to be an octopus. So we say that myocontrol is how we derive meaning from movement. So I'm going to show you now the demo part of this talk. And the first thing I'm going to do is show you our ability just from muscle mapping, how we can create a virtual hand. And what I want you to focus on isn't just that we can do like a gesture recognizer, is the hand open or closed, but the full continuous motion of the hand. This is a comically difficult problem. And it's really, like I said, the full dynamic range of motion, individuation of fingers, etc. You can see a device on my wrist there. It's an older device. Now, the reason...
Oh, it gets better. It gets so much better. So it's recreated a hand, and it's able to read basically in real time what that hand is doing in three-dimensional space.
The reason we did this hand is because we thought, well, I should say this. This is what we mean by intention. Now, notice I'm able to move the hand. My hand's not moving at all. It only cares about the nerve and what the nerve is telling the machine to do. Here it's doing the forces that I'm generating. No camera could ever decode this. We actually can do this across pinches. We calculate the forces across all the joint angles.
Calculating the force across all of the joint angles. Now imagine for a moment if they understood what the various changes are in the voltages, the cumulative voltages, the spiking that goes down your muscles, through your nerves, to do things like grasp something gently or very, very firmly. And what it would take to provide the similar artificial stimulation. Once you have those values and you have a system that can read and write, what do you have?
Of course, the reason we did this work for a hand and a virtual hand is because we think it's critical. It's the entry point for immersive computing experiences in augmented reality and virtual reality. Your hands are the most skillful part of you. That's why we want him back in VR. Here I'm going to show you a little bit more abstract. What we're doing here is showing you like that you don't have to actually move to do any of this stuff. He's moving around here, and we call these Star Wars hands. He's got this little cursor he's moving that's mapped to his wrist, and instead of actually moving to kind of play with these objects and move them around, he's just doing sort of like a Star Wars Emperor thing. He's just like slowly flexing his hand and getting control over these objects. We want to have this sense of empowerment for you, that you get magical control over things even when they're at a distance. It's not the things that are just in front of you. We want you to learn a whole new kind of control, not the control you learned when you were a year old stacking blocks, but instead if you were a Jedi trying to stack blocks a mile away from you.
I don't know if you guys have seen the VR functions that, or the AR functions that Space Command uses or other high-level agencies use, where they have complex problems and complex environments that they virtualize and then interact with in an augmented reality kind of a way. Well, this technology is directly applicable, very useful. If you were able to multiply somebody's brain, their output, their work output, after going through some basic training with this kind of technology, you would have a very much improved workforce, productivity, efficiency, whatever term you wanted to apply to measuring success or improvement. Because it's tapping into the mind, it's training the mind, and it's giving the mind a workspace that's beyond the limitations of the body.
This was from about a year ago. This is our first effort to do typing. I think that's me, you can see. Trying to say all your interface belong to us. This is the future.
That's kind of a creepy statement. All of your interface belong to us. What does that mean? That we have complete and total control of your reality? No, he wouldn't say it that way. He just means that he wants his company to be the interface between you and the rest of the world. Is that not the same thing?
Now, that were examples of some myocontrol, where we're mapping that out to muscles, and not just the movements, but the tensions that go into the muscles. This thing that we really never leverage in computing experiences today. Here we're doing something way more abstract. I don't know if the sound can be brought up on the presentation, but if it can, please bring it up. So here, this is my co-founder, Patrick Haifosh, another Columbia neuroscientist, and he's not moving. You have to trust me that there's a band on his wrist right there, but he's playing Asteroids on a phone, the old arcade game Asteroids. So this is a game that has 2.5 degrees of freedom. You have to push buttons, you have to fly around, change the thrust vectors, move left and right at different speeds, and he has full control and he's not moving. He spent about 60 seconds training the machine. I want to emphasize this. This is not you learning how to control. This is you telling a machine how you want to control it. And that is the fundamental thing we've screwed up for the last century.
Did you catch the 180 sales pitch right there? So you saw the guy's hand there, and he's literally just imagining moving that thing around in a video game. So when we think about automation, when we think about augmentation, when we think about everything being connected and virtualized, being able to be remotely viewed and monitored, including people, what are we doing here, folks?
Our interactions with machines, constantly improving the machines and asking us to learn them, not the other way around. Neurocontrol starts at the premise that you train a machine. I think this is exotic, and if your minds are not blown by that and a person not moving. I will tell you, sometimes this is the worst technology in the world to demo because it's just a video of a person not moving. But that should be the ultimate goal. This is our work to map this to different robotics, and here's the first biomimetic one, and then I'll show you an abstract one after this. This is Adam Behrensweig, also a Columbia scientist, and doing a little hexapod and mapping it for full continuous control over these things. Now the next thing here is, again, you can move that hexapod. You can move a hexapod with just a joystick, but why would you do that? What you really want to do is do all 6 fingers, but you only have 5. Well, that's where neurocontrol comes through. We can solve that problem somewhat trivially. This is him taking care of himself, as he should, with a 7 degree of freedom, $50,000 Canova arm as a back scratcher. There we go.
So the applications run the entire spectrum. There's immense opportunity here for tremendous innovation. The world's going to change one way or another. It's going to change one way or another. But at some point, that thing on the wrist, that's going to be a problem. It'd be so much easier if it was just a tattoo or, something under the skin, subdermal injection, or maybe it's just nanobots in your bloodstream.
And the next one, this is just a little continuation of that, where he's doing object manipulations. And you can think of this as, how would you train a robot to do something? One of the hottest topics in robotics is pick and place, and one of the hotter topics is actually having them imitate humans and learn from humans about how to do things. Here, we're mixing biomimetic action, the movements that he's doing, with things that are more synthetic. Remember, that thing has like a 360-degree rotation across each joint. A human body can't do that. He can still control it through all of those motions because of neurocontrol, because we're not trying to just map to what your hand is doing. We do a mapping to what your neurons do, and we basically don't care about this little device at the end of your arm. We care about what your neurons are doing. I want you to imagine for a second where we're going with this technology. Obviously, we'd like it to be something that just follows you around all day. It's just part of you, integrated into you.
Part of you. It's part of you. It's integrated into you. Did I mention that Facebook bought this company? I think I did.
Or onto you, I should say. The goal is for you to be the universal controller, not to have a universal controller.
The goal is for you to be the universal controller. Or is it the goal is for you to have a universal controller so that you can be remotely interfaced with? It's a two-way street.
I want you to imagine like your phone just being a dumb screen as opposed to something you have to actually do something to, but where you have incredibly fine control over everything it's potentially capable of doing. It would be nice to actually write something on a phone rather than jot down a 10-word message because I've run out of steam. I want you to imagine what it would be like to actually have, say, a new Apple Watch where you're just one-handed writing a quick message there. You're not talking to it. You're not having to type. You're just doing it out of one hand quickly.
There you go. First step. See why Facebook wants it? As soon as one gets it, they're all going to get it. Why did Google buy Fitbit? Because these are the interfaces of the future. Tapping into the nervous system not only medicates you, but it provides instant connectivity to you. I'll say that again. Tapping into the nervous system not only medicates you, it provides instant connectivity to you. Perhaps even both at the same time. Hashtag telemedicine. Make sure to wear your frickin' mask.
And then moving on to your next goal. This should be always available. The keyboard should be you. You shouldn't have to go learn 52 different keyboards. I will tell you that typing thing that we showed you earlier is actually really fun. It was crazy to have it, like, experience it the first time. And it really feels like it's your personal keyboard, like something you've never experienced before. We imagine, we imagine a new kind of productivity application. Imagine an architect working in AutoCAD, but instead of going to the palette sequentially to pick different interactions, instead they're blending all kinds of modalities together, the color picker and a rotation scheme all at the same time and simultaneously with full high fidelity control.
Oh, you mean like a active controlled hallucination? Moving things around, orienting them, changing the colors, creating different schemes, different mock-ups, all simultaneously. High fidelity control, you say. High fidelity? Oh, should we bring up the Freer Logic patent that discusses being able to interface with the occipital cortex, I believe it was, the visual system, and language system, to transmit thoughts of another person into the brain? How does that really work? You hear a word, you visualize it to some extent, don't you? You process it, smash it up against what it means to you, ultimately decide what it means to you, and then that becomes its own neural process, its own signature. This dude's talking about completely immersive augmented reality. Granted, you saw a picture with glasses on, like a HoloLens. But this is just one piece. Companies like Facebook would be looking at all of the pieces and seeing what they look like all together, kind of like DARPA. Wait a minute, aren't they the same thing? Or was that Google that was DARPA?
I think this has enormous implications both for productivity, but also just the joy of work, making it human-centric. So I'll leave you with this. I'd ask you, what would you do? What would you dream about if you had more control? More control over devices, where you didn't submit to them, but they submitted to you. We're Control Labs. I would be remiss if I didn't mention that we are actually shipping this technology to developers in January. You should go to our site and sign up for a developer kit if you are super interested in it. If you're a student, you should submit a job application. We are recruiting aggressively. We're a company of 45 people. We are very well funded. We are looking for the best machine learning, neuroscience, and design thinkers in the world. Thanks much.
So there you have it. We have not enough time to watch more of these. Let's watch this one.
Humans and machines have been merging for thousands of years. Right now I'm wearing shoes, I have a microphone on my jacket. We all probably used our phones at least once today. And we communicate with the augmentation of all sorts of amplification and even translation technologies. You can speak into a machine and it'll translate the words you're saying in nearly real time. So I think what might be different in the years to come is a matter of degree, not a matter of kind. One concept that that I think is emerging is what I like to call the brain coprocessor, a device that intimately interacts with the brain. It can
A brain coprocessor, a device that intimately interacts with the brain. Well, we've seen a little bit of that, haven't we?
upload information to the brain and download information from it. Imagine that you could have a technology that could replace lost memories or augment decision making or boost attention or cognition. To do that, though, we have to understand how the brain works at a very deep level. Although over 1/3 patients have had brain implants or neural implants that stimulate the nervous system, so far they've operated in an open loop fashion. That is, they drive activity in the brain, but not in a fully responsive fashion.
So he's talking about an open loop system. Computer tells brain what to do, brain does it, doesn't really provide any feedback to computer system. Open circle. We're moving into closed loop systems, so let's see what that is.
What we want to do is to have bidirectional communication to the brain. Can you read and write information continuously and supply, maybe through coupling these interfaces to silicon computers, exactly the information the brain needs? My hope is that over the next 5 to 10 years, we're going to get deep insights, thanks to our technologies, into how brain circuits compute. And that will drive the design of these interfaces so that we can deliver information to the brain and record information from the brain using the natural language of the brain, reading and writing information in a way that augments, for example, the number of things you can hold in your mind at once, or the ability to recall things nearly perfectly.
Folks, this stuff is going to be around when young children grow up and become adults. It's going to be here. The way we define productivity, the way we define interconnectivity, the way we define things like intimacy are going to be codependent and or interdependent on the internet. So better hope that your respective militaries have their population's best interests in mind. And the United States military, you better hope that they're upholding their oaths to things like the Bill of Rights and the Constitution, regardless of whether or not they forego those liberties and those protections while in service to this country. It doesn't mean that they don't have the obligation to ensure that they are protected, even in cyberspace, even in outer space.
Which is, not an ability so different from looking something up on a search engine on your phone, right? So I think what's going to happen is a continuation of this trend. And I think a lot of people like to talk about artificial intelligence right now. Artificial intelligence, as it stands, is based on a lot of concepts that go back many decades, that build from some very simple observations about the brain. What might AI do, though, once we have incredibly deep insights into the nature of creativity and ethics and other things that the human brain seems to be uniquely equipped for? I think once we start to couple artificial intelligence to the brain that can really augment these uniquely human capabilities, it leads to a new era of what you might call hybrid intelligence.
Are you hearing this, folks? Coupling artificial intelligence to the brain, augmenting intelligence, creating hybrid intelligence.
So it won't just be AI running away in some positive feedback loop. It won't be humans upgrading themselves in the absence of coupling to the world, but I think it'll yield a new kind of symbiosis. And I think that's probably the best possible path. And it's also already, if you look at how people operate in the world, what seems to be one of the most prevalent models.
So, Let's, we have about a half an hour left. Not really sure what we should do. I guess we can look at some of these articles on the Vegas system, because the rest of these videos I think are too long. Yet they're very interesting. Implantable and injectable wearable devices for affecting your neurology. Neural dust as a platform. Let's watch pieces of this, because this is it's an hour, but we'll see how it goes.
Well, good afternoon. I would like to welcome you all to this presentation. My name is Kostas Panos. I'm a professor of EECS and director of CITRIS and the Banato Institute. I would like to also welcome the people who are watching this online, including those on the other organisms. He's known as one of the co-inventors of neural dust, an ultrasonic interface for vanishingly small implants in the body. His group is also known for developing the world's first remotely radio-controlled cyber beetle. You should have seen that. I mean,
radio-controlled cyber beetle. This guy's from Berkeley, by the way, the one who's going to talk here in a minute. Radio-controlled cyber beetle, and he co-developed ultrasonic neural dust that can be implanted next to a nerve and with ultrasound energy power the device and modulate the nervous system.
It's still on YouTube. It's quite amazing. This was named as one of the top 10 emerging technologies of 2009 by MIT's Technology Review, Tier 10, and was in Time Magazine's top 50 inventions for 2009. Michel received his BS from Cornell, his PhD from Berkeley, under Professors Roger Howe and Professor Jay Kisley. His thesis work led to the foundation of Microreactor Technologies Inc., which was acquired in 2009 by PAL Corporation. Michel is a senior member of the IEEE.
Hopefully that's the right volume. They'll tell me otherwise inside. Okay, so we have, I figure, about 45 minutes, and I thought I'd give you an overview of what motivated the Neural Dust technology platform and some of the thinking behind it, where it is today and where it's going tomorrow. If those of you that saw the Bears talk, this is essentially the Bears talk, except I changed Bears to CITRIS about 30 seconds ago, so about 5 minutes ago. So if you get up and leave, I won't feel bad if you want to watch it again. Okay. This has been an extremely fun ride for about 3 years. It's very interdisciplinary. I want to point out Jose Carmena, Elad Alon, and Jan Rabai, who are the other principal investigators, all colleagues here at Berkeley. Jose is a world-famous leader in brain-machine interfaces. Elad and Jan are world-known for their circuits and other technology developments, and Jan has been a pioneer in that area for many years. DJ and Ryan really are the two work. There's a Journal of Neuroscience Methods paper that then otherwise, but I think it's good to keep them separate. And both of them really go back to Jose Carmena's work and his field in brain-machine interfaces, and Jose's been talking about this for a long time. So if you look at how we interact with our technology, right, you have a very sophisticated system up here, and you have very sophisticated systems here, and the way we communicate with them in both directions is extremely low bandwidth. And so the most blue sky reason for doing this, and I will admit it is blue sky, I don't want to give anybody any sort of false hope, is that we could build direct connections to our technological gadgetry through brain-machine interfaces.
Yeah, so this is Berkeley, Cornell, MIT. Those are the names floating around. The last video was Columbia and others. What we saw were wearable devices, the interface, read write through the nervous system. This guy's talking about things like neural dust doing the same thing. Don't forget about Mr. Lieber Dr. Lieber. And what he was doing.
Okay, so that's an overriding desire, I think, more on the science fiction side. On a more realistic level that grounds us in problems that exist today that are readily addressable by this technology and you will see over certainly the next 6 months to a year, there's going to be some very interesting announcements, and then over the next decade you're going to see quite a lot of work, is the sense that this could help a lot of people with certain motor and other disabilities. And so
there's your sales pitch, right? This is where they get all their money. This is how these technologies are developed, playing on the heartstrings of the public to provide the funding to then develop these types of technologies, which are then provided to the public, of course, at a premium once they've been developed with public money. So
let me talk a little bit about the two areas where the two subfields that have emerged in this area. The first, which is I think nicely encapsulated by this figure from Miguel Nicolas' paper from a few years ago now, is really encapsulated by the term brain-machine interface. And it's based on quite a big literature now that has shown that if you can take recordings from the cortex, whether you're looking at spikes or other variants of that, and you are taking those, running them through some filter, some algorithm, increasingly, of course, this is all machine learning based kind of stuff, and using that, decoding that, using that to drive some prosthetic, here shown as an arm, but it need not be an arm, it could be an exoskeleton, it can in fact be a speech prosthetic, it could be quite a number of things that essentially perform some function which the user is aware of how well that function is working. What a whole field has emerged around the idea that you can then train on this loop. So say I'm trying to use a robot arm, over weeks of training, my neural net will adjust itself to do this better. And of course, in modern brain-machine interfaces, the system itself is also adjusting. It's a two-learner system. So the desire to do this is a big motivator for technologies today.
We're going to pause. We're going to skip.
Demonstrated in humans. Academically and in companies, it's quite a bit ahead, and I'll show you that in the next few slides, but this is the grounding of reality today. Now, there are a lot of ways of taking data out of the brain, and I can't talk about all of them. I actually have a tutorial I give sometimes, and it's like hours long. I have to go into a lot of details, but suffice it to say that somewhere between EEG, which we all know sits outside the head and doesn't usually require any intervention clinically, but is very low resolution and really not very good for very serious clinical stuff, with some exceptions, but generally it's a very crass thing, down to what I described, which is getting right into the cortex next to a neuron and recording that, is a wide spectrum of interventions which my group is involved in, and we don't quite have enough time to talk about it, but I'm happy.
Yeah, so the Air Force document that we looked at, should we bring it up? I'll bring it up real quick. We'll likely come back to this neural dust. Where is it? It is here. No, it's actually under cyborg cells. So this document is exactly what this guy's talking about. If it'll load. Getting down to a single neuron and taking readings. What does that look like? What does that mean? While that's loading, cyborg cell molecular nanoscale circuits for active control of cells. Harvard, Charles Lieber, Air Force Research Laboratory, the abstract of this thing. The goal of this work is to develop molecular nanoscale circuits that control cells via external radiation. That would be radio waves, millimeter waves, or other types of waves, external radiation. We develop silicon nanowire probes as platform elements of these circuits and demonstrate their insertion into single cells, followed by stimulation to elicit cell signaling. Cyborg cells, yes, cyborg cells. Finally achieving a scalable modular nano device platform capable of recording high amplitude intracellular electrical signals in electrogenic cells, things like neurons. In parallel, we develop a conformal deposition technique and site-selective deposition of polymers to modify probes, and an approach to decorate nanowires with heavy metal-free quantum dot emitters that provide strong macroscopically addressable and reproducible nanoprobe emission signals. So here's the document. And if you go to humaninternet.org, you can download this document. And it was a 3-year program. It ended in 2018. And it goes through what Dr. Lieber, one of the projects Dr. Lieber was working on, right? And what that is to create these pieces of nanotech that go down to a single cell level, infuse into and through neurons, whether they be at the synapse or actually embed inside the neuron. See here it says internalization. You see how it's doped with these little spiral of Christmas lights? That's likely biomaterial, bioconjugated material, so that it will be accepted and not rejected by the cells. These are actual fluorescent microscopy images of this stuff inside of neurons. So we will go back to this video here in a second. But when we look at these technologies that they're rolling out in, cute and fluffy videos, like, hey, look at this cool watch. You're going to be able to interface with your computer with your watch. Or, hey, this neural dust, this smart dust, it's still a surgery. It's still got a microchip on it. We're looking at these for brain-computer interfaces. Well, you've got the Air Force working with the guy who has been working with China for the last decade, doing this stuff at the nano scale. Successful projects funded by the Air Force to do the very same things, reading and writing to the nervous system and the brain. And in this case, doping the nanotech with biologic material so that it can be targeted and steered into the right location. It talks about that in this document. So, with the remainder of the time that we have,
happy to discuss. Just be aware that there are a lot of ways that people are attempting to take data out of the brain and put it back in. But the one I just showed you, the arrays look like this. This is it should have a citation, I apologize. This is from a 2010 review paper in Frontiers of Neuroscience, which is very nice. And it shows you all the different types of shanks that different groups have made. And these things, which are on order of a millimeter long and tens of microns wide usually, get pushed in, as you're about to see here. This is an image of these arrays about to be pushed into the cortex, and you can see all the vasculature under there. That'll matter in a minute. But they all have different, ways of doing this, but you can kind of get a sense of what they all look like. Okay? So let me skip this slide. So what do you want when you build one of these things? Right? If you're building either the thing I just showed or very similar technologies for peripheral nerves, or you're trying to wrap around a nerve or go into a nerve. Well, whatever you're building better be able to detect the signal you want, and that might vary. There are different types of electrical information that are worth collecting for these interventions. You might want to stimulate. You might actually want to apply electrical energy to the nerve or the neurons to get something out of it. I'm going to come back to that at the very, very end. You need to, of course, process some of this stuff very close to the signal. You have to do a lot of data conditioning and front-end amplification to clean it up. You, of course, need to get power to these things. We're going to talk about that in a minute. That's really the big source. So you need to talk to them. You need to talk to these arrays and these signals. And all the while, it's got to be small. It's got to be biocompatible, which is where we're going to go in a minute. It's got to be safe. And lastly, it's got to, hopefully last quite a while. Well, it doesn't exist for lots of reasons. It's actually a really complex problem. So, but we can hit the big points. The organism, thinking about it from the organism's perspective. So, any area of your brain that is heavily, is dense with neurons is equally dense with capillaries, with blood vessels, because that's how the neurons, get their food. And this is why MRI works, because MRI is not measuring neural activity, it's measuring oxygenation locally in little areas, because that's a proxy for neural activity, right?
So what he just said there is huge. Being able to measure blood flow in the brain or changes in the blood in the brain also provide an interface, whether it be only for reading or not. When you combine those techniques with other techniques, you get a read and a write, such as using resonance techniques to stimulate the brain, and then potentially an MRI style technique to read what's going on with the changes that you're making in the brain. And we'll watch a video from Mary Lou Jepsen here, upcoming shortly, where she's developing technologies that are wearable to do just that, read and write to the brain, using things like light and ultrasound in something as sleek as a ski cap. So no operations needed. You can just go buy one from your favorite retail/tech store as time goes on. She's actively working on this technology now. And she came from Google and Facebook and MIT. She's an expert in optics and spent roughly a decade in China going through their manufacturing functions over there. So she knows the industry very well. Maybe we'll front load some of her videos here very soon.
And so what happens when you shove these things in the brain is you go pop, 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 and you microembolize everything down as you're going down the stack. All those little vascular things get basically exploded, and then they get cleaned up most of the time. And so you can imagine that that's going to recruit a lot of local and systemic responses by the body. The body gets pretty pissed off when you do that. And one of the ones that has been recognized for a very long time is that you get encapsulation of the implant by glial cells. It's called gliosis. It's sort of this scar tissue idea. Now, someone showed, and by the way, let me add, and these are stiff, right? These are pretty stiff implants. And nothing to do with this sort of fibrous gelatinous nature of your cortex. And so someone showed quite a while ago that if, it was Daryl Kipke, in the mid-2000s, that if you can make your implant small enough, he was his group was introducing shanks, just like the ones I showed you. What they showed is if you shove in 150 micron wide shank, a millimeter long, versus a 50 micron one or a 60 micron or smaller, the very small ones didn't effectively, as far as they could tell, get very noticed by the cell response. We're
going to skip.
Just me trying to convince you that this works. I always say, stop checking your email. This is like the only slide you have to look at for the whole talk, and you can go back and check your email on your phone.
So a little bit of groundwork, what this guy is going to talk about, existing technologies and what he's working on. Neural dust system, minimally invasive when compared to stabbing pins into your brain. Right?
Because I'm in the audience, and that's what I do when I'm in the audience. So anyway, so what works? What works really, really well is ultrasound. And the system is pretty straightforward. The idea is pretty straightforward to explain in this one cartoon, and the rest is just me trying to convince you that this works. So how does it work? So it turns out that electromagnetics aren't going to work, but ultrasound will work. And the reason ultrasound will work, and I'll put up, somebody's taking a picture of it, so I'll put up all the mumbo jumbo at one time. Why does it work? It works for the same reasons that it didn't work in electromagnetics. Sound is slow, so the wavelengths are dead on. At 10 megahertz is about 175 microns that you need. It's perfect. And medical ultrasound goes all the way up to tens of megahertz, so it's perfect. And your body actually is reasonably transparent, with the exception of bone that I'll come back to. It's reasonably transparent to ultrasound. The loss is much, 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 much lower. Okay.
So I agree with what he's saying. Ultrasound is super efficient. They can make ultrasound with electromagnetics. It's called thermoacoustics. They can do it with light. It's called optoacoustics. And what that is it's the very, very rapid heating and cooling of tissue. Not that it damages the tissue, but nonetheless, it expands and contracts the tissue because it's primarily made of water. So you excite and you heat up the water. It expands the tissue and contracts the tissue and creates sound waves as it passes through the skin, the skull, brain matter, etc. So he's leaving that part out, and it's not as efficient, but it still works. That's why you have the voice to skull technology that the Air Force uses for things like covert communications. And those patents are available. I haven't posted them on the site yet on humaninternet.org, but I will. That's upcoming.
Okay. And so what happens if you put these two things together is that ultrasound is actually a really nice medium to power up and communicate stuff that is really tiny. So what you do is you implant a little piezoelectric crystal and you cut the crystal so that the thickness of the crystal is lambda over 2, wavelength over 2. So what will happen is you'll set up a resonance in the crystal so the crystal will wiggle. If you send in ultrasound from the outside at the right frequency. So you send in ultrasound from the outside, this thing's outside, it comes in, hits this thing, wiggles. Now what happens? A couple of things. Whatever you put here, even if it's not a special type of crystal, energy will bounce back just because it's hitting a dissimilar interface. I'm gonna do something unprofessional, pull my shirt out. So anyway, energy is bouncing back. And you can see that. You can listen for that outside. Now, a couple of other things happen. One is, if this is a piezoelectric crystal and I have electrodes across it, when this thing begins to ring, it'll produce voltage across it and it'll be able to drive a current, which means that I can use that to power something next to the crystal implanted in. It's a mechanical to electrical transducer. And
so they've got nanotech that does this all in a single piece of nanotech. Piezoelectric material that then converts into a voltage that then allows photons to come out of nanotech. So the technology is beyond what this guy's talking about. This is just one research study that kind of breaks down a little bit of the science of how this stuff is possible in a very, very small form factor.
And the other way around. So that means that I could use this essentially to power something connected to it. Now here's the trick. The trick is, if I can build some circuit here just shown as a variable resistor, which it isn't, but just something, if I can build some circuit that as a function of a neuron firing or some other interesting signal can modulate the impedance across this crystal, the amount of energy reflected from this crystal will change as a function of that. It's like a tuning fork that I tap when I want to, and someone can tell that that's happening. So all I have to do is sit out here, hit it, and listen. And as long as I know what's going on, and if I can in fact do this, I can reconstruct what's happening inside the body very nicely, very elegantly. You can also see that I drew this in an analog way. You can make this digital. This is very, very similar to the way your subway cards work, near field and RFID. This is just done with ultrasound. You can sit there and encode ones and zeros if you want. You could build all sorts of stuff around this platform. So that's the whole idea. That's it. So now what I want to do.
So that's it. We're gonna take the last 5 minutes and kind of chill out. But what he's saying is they can use very sophisticated, similar type technologies to create a 1 and 0 input output in very, 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 very small form factors around neurons, which are in the nervous system and or the brain. And when we look at the stuff Lieber was working on, this stuff can be absorbed any way, anyhow. It can pass through cell membranes and not be rejected. It can move about freely throughout your body. It doesn't have to go in and be placed somewhere and attached and stay there. It can go in any number of ways. This is the world that we live in today. And that the algorithms and the technologies exist in order to drive these things. So just be aware. Maybe at some point we'll go look at electroporation and microneedles and all of the stuff they're going to be using for vaccines, because this all ties together. All of it ties together. They tell you a lot about one piece when they can apply it with the things that seem like they have to be done with surgery and you have to have a specific set of conditions, but then they'll tell you about other pieces just because, hey, this is cool technology. And I think it's incumbent upon us to figure out how these things fit together on our own so that we can start asking these questions, wondering just exactly what's going on. So here, we'll cover this real quick. This is something DARPA's working on. Moana, speed of thought, a link between brains. Optical source detectors, magnetic stimulators. DARPA funded a 4-year project, headset technology that can directly link to human brains. This was published May 23rd, 2019. Rice University in Texas, part of a wider DARPA-funded program developing wearable interfaces for communicating with the brain. In 4 years, we hope to demonstrate a direct brain-to-brain communication at the speed of thought without brain surgery, says Rice's Jacob Robinson, the lead investigator on the $18 million project, which was announced on May 20th, 2019 as part of DARPA's next-gen non-surgical neurotechnology, their N3 program, which we've covered in great detail on this show. We will recycle that information because we've gone through a great deal of information since we've gone over that information. We've been through genetic engineering, we've been through nanotechnology, we've been through now some nerve stimulation, all of which are requirements for the N3 program. Speed is key, Robinson said in a statement. We have to decode neural activity in one person's visual cortex and recreate it into another person's mind in less than 1/20th of a second. The technology to do that without surgery doesn't yet exist, and that's what we'll be creating. Rice's Moana, magnetic, optical, and acoustic neural access device, will test techniques that employ light, ultrasound, or electromagnetic energy to read and write brain activity. Robinson said Moana's decoding and encoding technologies will employ viral vector gene delivery, genetic code, a technology in clinical trials for treating macular degeneration, blindness, genetic payloads, right? Artificial genetics, synthetic genes, foreign genetics inserted into the body, which differ for decoding and encoding, mean there are going to be separate genetic payloads, one which is designed to offer decoding of the brain, and another genetic payload designed to offer the ability to encode, to write information into the brain, will be delivered with the help of ultrasound to select groups of neurons in 16 target areas of the brain. The ultrasound creates what they call sonoporation, for example. And what that does is it temporarily opens up the cell membranes and/or the blood-brain barrier to allow this genetic payload to pass through in a targeted, steerable kind of a way. To read neural activity, the Moana team will reprogram neurons. They'll reprogram neurons to make synthetic proteins called calcium-dependent indicators that are designed to absorb light when neurons are firing. Rice co-investigator Ashok Viragaravan said red and infrared wavelengths of light, the stuff they use for Face ID, can penetrate the skull, and Moana's device will utilize this. Maybe Apple does too. The optical subsystem will reportedly consist of light emitters and detectors arrayed around the target area on the skull cap. Well, you've got it shining in your face because it's infrared. You can't really see it pulsing, can you? No, you can't. We don't see infrared. And here's a good little diagram. Brain A, brain B, says house, says car, sees car. Talks about the rest of this, but we are out of time. So come back in 4 or 5 days. Is there anybody else in here?
Nope.
Are they supposed to be?
Huh?
Are they supposed to be?
Mm-mm.
It's you?
Nope. Yeah.
Oh. Well then, what do you want to talk about?
I don't know. Did you want to get some water or something? Did you need to?
Are you kicking me out, Crystal?
No, absolutely not. Never.
No.
Never.
Yeah,
No, I wanted to, just usually,
I will in a minute, yeah. For sure.
Great show. Scary, but no,
yeah.
I'm scared. Not scared. Well, it is scary, but you know what I mean?
Building layers upon layers upon layers.
It's just crazy how, they can insert someone else's, and where you're talking about brainwaves into someone else's, and that was just crazy how the other person can move. And I know that was like a little bit far back, but someone else can move someone else's arm.
Yeah.
I don't know. Gosh.
Well, yeah, that's, that's just somebody with some basic neuroscience background and some electronics experience. Can you imagine what DARPA and groups like Google and Facebook are working on? Systems that fuse together the satellites and the cell towers and all the mobile devices all around with all their different energy emission capabilities, coupled in with their AI and their cloud-based systems and their complex networking algorithms and all of the sensory feedback that they get. I mean, what we saw is, it's everything I can do to find just slices or slivers of information that kind of give us a peek through the veil that is the future of the internet.